morning，这样子啊？我手录没开的，可以热火。底下那稍微聊天一点。哎，我用这个。就你一个人来，啊？嗯，没有睡醒啊？为什么？问题的问题。嗯，这个问题是我们说的。还是好的一个好一个。那么，蘑菇啊，什么？
做要唱歌。
跟耶稣看，耶稣讲那个，
讲耶
耶稣
稣，
现在是佛教，Christian，要不要会给他们？
什么？
然后我的泡，
没有啊，啊，他们写唱歌。
我昨天
有 presentation 啊，
发梦的时候，发梦到那个观音的那个一个打架，然后一个鸡舍，然后什么鸡舍，
好像有听过，
看不得。
听不懂。好，
呀，老师不要去考，你自己
说没有。
看你这小白文，连环也被你打得过他，
哎，
有机会谈出来的。
Okay, before I start, right, I want to say some update to the lecture note. So, for example, please note that there's an update to this page here. Okay, the branch multiplier. Hello. And when you started this slide, I'll update. I already updated this slide. Okay, this is the Lagrange multiplier lecture 21. This one. Yeah, I mean, take note of this question. 71. Lecture 21. The function I used last time is not complete, so I need to add a square root. Okay. Yeah, if you have problem understanding, then I can bring out next lecture. Yeah. Take a note. Yeah, I posted it.
Yeah, 讲 update 吧，我就没有出入。哦，
这地方
我知道没有出入不会。
learn this one they have some not enough time. Partial differentiation. The last part, Lagrange multiplier. Okay. Okay. And then another update is at this one I haven't paused out yet, but I will post it soon. Is the update on this question. Okay, so this question asks you to change the order of integration. But this one is kind of tricky if you choose one of the way. Okay, yeah. So so you can see that if you swap to dy, dz, dx, right, the inner limit here, right, is determined by two functions actually. Okay, this is not a usual example here. Okay, but how to get this inner limit here? You need to really slice it. You can see that the y is depending on z and x. If you choose different slice of x, you have different y. Okay. And I also draw out another diagram. I think this diagram will be this domain will be easily chosen by you, I think. But this has a different picture if you use this domain here. This is I guess, should be the hardest among all the examples here. Okay. I'll post this up later. You can have a look. You don't have the function to integrate. They just ask you to change the domain order of integration. Okay. Yeah, take note on which slide got changes, then you pay extra attention. Okay. If you got problem, then bring it up next time. Okay, clear. I will post this soon. I will post this up. I'll post it soon. Okay. If you go through my slide last time, right, I add up the summary section for you guys for part multiple integral. Let me see. Okay, so I add up the summary for you. Okay, definition and then what sort of theorem at the end of last lecture notes. There's some property, then and then I draw some shape here to show you what kind of shape use which relevant coordinate to integrate. Okay, if you got some rectangular shape, you should use the regular coordinate. If you got some polar shape, you should use the polar coordinate. Okay, similar to 3D case. If you got sphere or cone, ice cream cone, or boxes or cylinder, then you use a different coordinate to calculate. Okay. Yeah. Okay. Any question on previous chapter before we go to the new chapter? You start revising or trying the example? Not yet. There'll be quiz coming soon this week, right? Wednesday to Thursday.
Can you teach me how to do this question?
Okay. Huh? Oh yeah, tomorrow we got the max seminar by MNT student, also calculus too. So everything you have learned. So how to apply on real life. Okay. It will be start 1 p.m. At where? At A1 A4G01. Yeah, the lecture hall. Again, you could come. I'll post out the schedule soon, and then you can have a look. Yeah. You can come and ask question. You can come and ask AI question also. Can. Oh.
我觉得这是一个好方法。
Okay, later can discuss. We still got catering also. Catering? Huh? No lah. No. I mean, I want to find someone to do catering. Catering. Okay. Any question on multiple integral, our previous chapter. Yeah, I think the hardest to imagine one is a triple integral and sometimes the Jacobian transformation. So try a few more examples to help you. And I also posted out the Aiden's book, right? Aiden's have solution to all the question, so you can read. Very high, is it? Oh, okay. Step very long. I see. That's what I used when I was studying. Huh? So yeah, I posted out the solution manual. You can just read it if you like.
然后里面就画对 this is bullshit， 然后 this is bullshit， you can skip this。
Okay. Okay. So we start new chapter. Okay, let's start with a new chapter. Okay. A new chapter is quite closely related to physics. Yeah, closely related to physics. Yeah, very closely related to physics. Yeah. Okay, so let's see what's the object we are going to have a look. So okay, so we have gone through parametric curve. Okay, we have gone through parametric curve. Okay, what are parametric curve? So we have a map from R to Rn. Okay, for example, R2 or R3. Okay, what are these? Really, you should think of it as geometrically. Okay, not just number, input, output. Okay, typically when you are doing AI, right, you guys just care about number, right? You just input number, then the function output you number, or the code give you number, output number, right? Just number. So really, you need to imagine this, okay, to get a better idea. So R to R2 tells you how the R sit inside R2. Okay, how the real line sitting inside R2. Okay, if R in R3, what's the diagram here? So you imagine a particle running inside the 3D space. Okay, so there's the idea, philosophy that our Earth is not flat. Is what's the word? What's the word? Huh? What's Shini in English? Shini. Huh? Shini is what? Virtual. Yeah, virtual. Okay. I mean, yeah. So they're trying to build a world using computer or AI. Okay. Yeah, this is one of the philosophy. Okay. Okay. Next, parametric curve, and then what's next? So next is the series stuff. Okay. Or sequence. Huh? Useful. So not useful, but let's go through what we have learned and then we try to predict what is going on. So we have sequence is n to r. Okay, how n sit inside r. Okay, how natural number, discrete number sitting inside a continuous space. Next is series. Okay, series is just real number to real number, but infinitely many term, right? Infinitely many term. We test the convergence stuff. And then And then we go to this surface or solid, right? We look at the calculus on surface and solid. Calculus on surface of solid. What do I mean by that? We look at the graph from Rn to R. Right? We look at the map from Rn to R. But we look at the graph of F. Okay, we look at the graph of F. So I have a R2. Okay, I have a R2. I have a plane. Okay, tell me every point got what are their height? Okay, I give them the weight. Tell me what are their height. Okay, so for example, something like this. This is a plane. Okay, I can lift it up. Okay, lift it up in the middle. So let me draw something. I can lift it up in the middle and then go infinitely. Okay, so this is what's this graph? So this graph is e to the minus x squared plus y squared. Okay, so I have a plane. I have a plane, right? Okay, I have this plane here. Okay, and then I lift it out in the middle. Okay, so this is the function e to the minus x squared plus y squared. Okay, I lift it out in the middle. Okay, yeah. R3 to R. R3 to R, we can't really imagine, can't really draw anymore. Okay, R3 to R. Because the graph live in R4. Okay, so this graph, maybe I put G here. This graph live in R4. So what do you do in that topic? You see how the surface of solid get curved. Okay, you look at any direction, so direction derivative. How slope is it? How steep is it? And then you calculate the volume using multiple integral. Right? Okay. So what sort of possibility you can do on function? Look through this list here. What other possibility you can do? What sort of domain or codomain you can do function? Any other possibility you can do? What do you mean I combine everything? What sort of possibility you can do? Huh? Say who say something? You say something? R2 to R2. R to R2. We already got R to R2, right? Yeah, we already got R to R2. Yeah. What are other possibility we can do? Okay. What? That's half dimension, you mean? Half dimension. Uh, half dimension exists, but not in a vector space. We call something we call a category. Yeah, there's a category of golden ratio. Dimension of golden ratio. Okay, so half dimension. So what we are left with is going to different dimension. Okay, so Rn to Rm. Right. Give you a vector, you give me another vector. Okay. Rn to Rm. So actually these are all Rn to Rm, but we will look at a specific one, which is just Rn to Rn. Okay. Both of them are the same n. Okay. If both of them are the same n, R to R is a normal function of one variable, but we'll look at R2 to R2, R3 to R3. Okay. Give you a R2 point, give me a R2 vector. Okay, let's see what we are going to do here. So in particular, we will look at R2 to R2 and R3 to R3. Okay, this is the main subject in this topic here. R2 to R2 and R3 to R3. Okay, let's see how we write this function down. So this kind of function is what we call a vector field. Okay, so if you listen to the physicists saying vector field, vector field, vector field. So what's vector field? Vector field is just a function. Okay, later we'll see gravity. So vector field is just a function. So if I say vector field on R2, what does it mean? So a vector field on R2 is a function f that assigns each point in the domain in R2 a two-dimensional vector. Okay, so if I say a vector field on R2, meaning it's a function that takes in a point in R2, gives you a vector in R2. So I can extend this definition. What's the vector field on R3? Yeah, I give you a point in R3. Okay, you give me a vector in R3. Okay. How about R4? Okay, a vector field on R4 is just giving you a point in R4 and then give me a vector in R4. Okay, so we'll cover this. Okay, so this is an example of a vector field. Is this following the definition of vector field on R2? The function defined by fxy equals to minus yi plus xj. Okay, why is this an example of vector field? So you input a function, input a point xy. Okay, I give you a vector in xy. So do you realize that this is equivalent to the row vector minus y x, or you also can write it as a column minus y x. Okay, yeah. Okay, so this is a vector. So you input an element. So let's put point in R2. Okay, so you output a vector in R2. So far, okay? Okay, so I let you spend about 3 minutes complete this table here. Let you have some hands-on experience. Huh? Sorry? What do you mean? Bracket, yeah. Why? Okay, so I here typically refer to the x coordinate. J typically refer to the y coordinate. Okay, so there's a convention here. So I is the unique vector 1, 0, and then J is the unit vector 0, 1. Okay, so this is the convention IJK. Yeah. Why everyone becomes so excited? Okay. Okay, so try complete this table in 3 minutes. Have some hands-on experience on vector field. You can discuss if you want. Discuss with your friend.
看到比那天你参加你朋友会比他的那个暴露顺序哦，我怎么？那我感觉你是跟他有讨厌的啊？好的，好的，他就是采访人家。讲啊，
没有带衣服回去。
一点病都没有，都讲回去参加婚礼，电影课办吧，办8段去看的。
我们等用， 嘉语 not here. 林西城，林西城 here. 高飞，杭州，江宏宇，李杰，李培，李玉章，连叶，林天阳，刘佳琪，刘品义，应该说刘品义，刘夏红，龙凌波，凌波 disappear， 对，江瑜，玉林，彭玉林的念作语，杰森，那个，樱花那边，樱花说 disappear for long time， 邓子飞，裴武，西龙，宇轩，俊宇，俊宇，俊宇，子凯，这个初宇轩哦，谢宇轩，王宇轩，照片啊 ？What? You? Oh wait, I thought you are. Yeah, I thought just now you raised your hand just now. 施杰生 ，Yeah, 王宇轩，谢宇轩，OK， 谢宇轩，子凯，景荣，张云，金涵，应该说金涵第二，金涵第二，宜轩，康，OK， 这样子。All right. Okay, let's see. So what do you get for the first column? 0, 1. Okay, good. Second column. Next. What do you get? Negative 2, 2. Next. 0, 3. Next. Negative 1, 0. Next. Okay, next. Negative 3, 0. Next. 0, negative 1. Next. 2, negative 2. Right. Next. 0. What? Start already. Look. Yeah. I restart my share screen. Yeah. Okay. So what does this table doing? Okay, let's pick some point here. Okay, pick some point. So let's pick the point on the unit circle. Right. So let's pick the point on the unit circle. So for example, this 4 point here. Okay. So these 4 points lies on the unit circle. Right. Okay. So what is 0, 1? 0, 1 is a vector going up. 0, 1. What is minus 1, 0? Going to the left. Okay, going to the left. 0 minus 1 going down. Okay. 1, 0 going right. Okay. So let's plot this vector here. Okay. So there are 4 points on my unit circle. So 1, 0, 0, 1, minus 1, 0, and 0 minus 1. Okay, so on 1, 0, we have a vector going up like this. Okay. On 0, 1, we have a vector going to the left. On minus 1, 0, we have a vector going downward. And on 0 minus 1, we have a vector going right. Okay, so you can see that this vector is kind of like spinning the circle here. If you follow the arrow, this vector. Okay, so in fact, if you plot out everything, okay, you will see this diagram here. You could imagine if you put a dot, a particle on inside the plane, okay, this particle will move with this movement or that direction of the vector. Okay. Yeah. Okay. Anti-clockwise. Yeah. Is that okay? Okay. Okay. Yeah. So, some other example. Yeah. So this is it. So, any question about this one? No. Okay. So, give you a point, you give me a vector. You give you a point, give me a vector. Yes, so this is. Actually, you have encountered this function before. Do you know? What's the function? Huh? No, I mean example of vector field. Actually, you counted it before in the partial derivative chapter. Huh? What? Yeah, that's an example of vector field you learn. Do you know? Can you guess? Example of vector field you learned before. No. Vector plane. Vector plane is what? Vector plane. No, no vector plane. Vector plane is an equation. I want the function. You see this example of vector field before in partial derivative. Can guess or not? Huh? Gradient. Gradient, right? Gradient of f is a vector. Okay. So gradient of f, you input a point, you get out the vector. Right. Exactly the vector from Rn to Rn. Remember? So if your f, okay, if your f is xy, okay, what is gradient of f xy? Okay, this is just del f, del x, and del f, del y at xy. Okay, so this is an example of vector field. Okay, gradient is an example of vector. Okay, next. So there are some other vector field. For example, this one, x over square root x squared plus y squared plus y over square root x squared plus y squared. So why do I divide by this square root x squared by y squared? What is square root x squared plus y squared? Distance. Okay, distance from the origin or the length of the vector from the origin. So you scale every vector by the length. Okay, so that's why you can see that this vector on the point, right, have the same length. In particular, they are length 1. Okay, so these are length 1. You can see that everything is the same length. But here you see, some of them are long, some of them are short. Okay, but this vector field scale the length to 1. Okay, so every point you got the original vector and then you scale it to 1. So you can imagine that this is like the durian. Yeah, durian. Okay, so if you put your hand on the durian, right? Okay, you will feel the outward force pressing you radially, right? If you press on durian, you will feel the force from radial direction. Okay? Right. Make sense or not? Okay. Okay. So can you imagine if I change the sign to negative, what do you get? Okay. So you get the opposite direction of the vector. So everything will move inward if I replace it using minus. Okay. So if you consider this as 3D, this is exactly the Newton's law of gravitation. Okay. So Newton's law of gravitation. But Newton's law, there are extra scalar here. Okay, extra scalar here. So Newton's law says that the force is depend on the mass of two objects. Okay? Force is depend on the masses of two objects. So if two objects have large mass, then they have a strong attraction. Yeah, okay. So if you have greater mass, you have a greater force. You can say so. Yeah. Actually, this is quite true, you know. Actually, this is quite true. Actually, you can find that what do you say just now? People with what? Big body, yeah. This here say big mass. Big mass. Actually, we also find it quite true. So, no offense, but fat people are usually more optimistic. Okay. But this is Newton's law, right? But this Newton's law doesn't always hold true. Okay, it doesn't always hold true. Why? Because it's not just mass that governing the gravity force. Okay, actually, gravity is a result of geometry. Okay? It's a result of geometry. It's not just about force. No, I just want to share this. Yeah. Okay, so it's not attracting, but if you should think of the space as a fabric, and then fabric, you know fabric, right? Fabric, yeah, right, fabric. So fabric. So if you put a weight on the fabric, and then this fabric will like sink. Okay, one is sink, everything at the side will follow the trajectory of the thing. Okay, so you're like drop into the around. Sorry, take a blanket. Yeah, right. Right. Yeah. Okay. Even that might be not true because that couldn't explain what happened in the black hole. Okay, so we need some new theory again. All right. Next. Okay, so we reach this, the gradient of a scalar field. So what's the scalar field here means? So scalar field here means a function from Rn to R. Okay, so the output is R. So that's why it's scalar. What scalar means? The output is R. Okay, and why is it vector? Because the output is a vector. Okay, although real number is a vector, but we think that vector is a higher dimensional thing now for now. So why we use field? So this one is not mathematical. This is actually coming from physics. Okay, so physics people study with a field, so we use a field. Okay, so scalar field means a function from Rn to R. So the output is R. Vector field, the output is Rn. Yeah. Okay, so suppose F is a scalar field, and also F is differentiable. Then the gradient we defined last time is just the partial derivative, okay, at each coordinate. So del f xy is equal to del f del xi plus del f del yj. Or if you like, last time we used a notation of row vector del f del x on the first coordinate, del f del y on the second coordinate. Similarly, you can do it for three variable. Del f del x, del f del y, and del f del z. Okay. Okay, so now we don't ask you the gradient of a function. We ask you a gradient of gradient vector field. Okay, so this really mean the same thing. Okay, so this really mean the same thing. So same thing as gradient of f. So what's the gradient vector field here? Huh? What's the del f del x here? Uh, 2, 2xy I plus x squared minus 3y squared. Okay, so this is the gradient vector field. If you want, you also can plot out this vector field, how is it looks like. I think I have a software, you can play around with it. I put a link on the Moodle vector field. I think you can insert the equation and then the program will help you to draw it. See here. Okay. Okay, next. Next is what we call a conservative vector field. Okay, so when is it conservative? So a vector field is conservative when it is a gradient of a scalar function of a scalar field. So if the vector field equals to the gradient of some scalar field, then we call it conservative. Later we'll see how nice is this conservative vector field. So conservative vector field. And on the other hand, f is called a potential function of the vector field. Okay, so if this true, if this equation is true, f is called a potential function of my vector field. Okay, and then f is the gradient of f scalar field. Okay. Yes, for example, so we have this force here. Okay, c times r over r cube. Okay, c times r over r cube. Show that fx yz is a potential function of f. Okay, and then the question is f a conservative vector field? So maybe we can answer the later question first. If I already show that the vector field is a scalar, is a gradient of a scalar field, is f conservative or not? Is the vector field conservative or not? Yes, right. Okay. So if the vector field, if a is a gradient of a scalar field, then f is conservative. Okay, why is it true? This is by definition. Okay. Okay, so the definition of conservative vector field is you are a gradient of a scalar field. Okay, so let's see if this is a gradient of a scalar field. So we need to check. So to show that f is a little f is a potential function of the vector field, the big F, we need to verify what equation you need to verify to show that little f is a potential function of f, of big F, vector field F. What's the equation you want? What's the equation? What's the equation you want? Okay, big F equals to del F, little f. Okay, so let's check this. So, which side you want to do first? Right hand side, right? Okay, because this is the only place you can play around with. So let's compute this. What is del of little small f? So this is the gradient. Okay, what's the gradient here? So the gradient here is del f over del x, del f over del y, del f over del z on the respective coordinate. Okay. Okay. So what's del f over del x here? Del f over del x equals to what? Del of the whole thing c over, okay, let's write it in this form, maybe easier. C times x squared plus y squared plus z squared to the power minus half. Okay, so what do you get for this? You just get c times minus half times 2x over x squared plus y squared plus z squared to the power 3 over 2. Okay? So in other words, you get minus cx over 3 over 2 root of x squared plus y squared z squared. Okay? So you can see that this is this derivative is similar if you replace x with y, x with z. Correct? Okay, right? Because this equation is symmetric with the equation of f is symmetric to x, y, z. So if you differentiate any of them, you get similar result. Okay, let me size it. Okay, so anyone lost or not? Okay, so all together, what do you get? You get minus c over x squared plus y squared plus z squared to the power 3 over 2 of x, y, z. Okay. And then what is this? This is exactly big F. Okay, c over this factor x squared plus y squared plus z squared to the power 3 over 2 times xi plus yj minus z. Okay. Any problem with it? Any question? Straightforward. Later when we introduce line integral, surface integral, this conservative vector field will pop up again. I think in fact this is the motivation started by this physicists. And then look at the gradient, how the gradient change to the force. I think you can think of it as a field because you run on the field, right? Particle also run on the field. Right. Okay. Yeah, have a break. Let's break until 9 o'clock.
可以，等一下再讨论，可以。有点还没听到，待会没在，苏泽会上对，好像没叫。DFD 哦，你是后面，我还没叫一下，还没叫。
这个 scale 就把一个 point 作为
对
然后是一个
对对。
scalar field 是
scalar 一个对，没错。
为什么这个它这个一个 scalar，那它的 gradient 为什么会是一个向量的？
就是我们上课学的，就是这个，因为我们取的是两个方向
对，
，x 和 y。
那这个还是它的 gradient 不等于它的直接取了，就不等于它的切线。
不是切线，不是切线，但是不是说不是切线，是 directional derivative 才是切线。对，gradient 不是切线，gradient 是是那个 normal vector to 的 tangent。
它是在一维，它是一维会有讲它的直线，然后它的 gradient 就是个切线。
对，它 gradient 肯定是不，现在有两个概念，就是 gradient 和 directional derivative 这两个。directional derivative 是给你那个 slope。gradient 不是 gradient 记得吗 ？gradient 是那个 normal vector to 那个 tangent。
对 direction 才是 slope，它是一条曲线的那个
directional derivative。
direction 的。
对 derivative。
然后还有这个，然后我们手写是不是要加键符？
比较好。对，没错。
真的是60节都要讲了，还是
要
讲
怎么嘞？
就是那后面不是还有那个
哪个？
微分方程？对
对，
那就是我们什么时候课的就怎么上？就是什么时候能把这些内容全部结束掉？
我觉得1.5周可以结束这个，然后剩下可以在0.5周结束。
那我解课
所以大概
上场就是微个几啊？
算到下个星期。
上下一这个人
Daniel Robin Kevin 水龙钟豪一训学生管天开为邀請本德議會議孔明嘉盛 Bernice 文慶會後輕柔依照旨意認真認真簽名here OK 簽名認真凯杰凯杰
每次以为他解读错了。
亚美深航
够了。
TOT
我对这里还在敲木
有浮沉的王宇轩呢？王宇轩。
他说给200收费，
什么？
他收了给200收费。我们还跟你讲，他200收一起晚上。然后开始。然后我跟你讲，我拿皮蛋丢了。 他判我3次评级，他每次都会我上完课过去开打兵，我只是他的鞋子都没有看。我就找一大堆，我没有吃，我不要把它去。对，那天一个也是唱歌唱到啊，有发音，2个发音，发可跟发又修下来了，修什么？你需要什么？你修什么？啊，很自恋。来，看，来，我打开门来，来，我不打开门，看剧，看剧看。贾斯汀，
什么角色？
没有看过咩？贾斯汀，
我知道
贾斯汀啊。那个老师来修2句，不要害羞啦。
要还钱哦。
啊，要还钱，我操！
啊，那点不一样啊。
老师，你现在其实不会惩罚你，这样子。
等下你们有 presentation 没？
前面我妈你个不久吧？我好像蛮久了，不过我找不到 original。后面不要听啊！
这个这样有才。老师轮到你了，
到你啊！
不要交出去啊！你交跟你他。distinguish 的积分。
Okay. Yeah, so the plan for the rest of the lecture, right? We have 3 lecture left. 3 lecture left. So 4 lecture actually include this lecture. So 1.5 weeks we will finish this chapter, and then the other 0.5 weeks we'll finish all the only have 15 slides. If we finish earlier, maybe we do some revision, or I just give some tips. So which part is important? Do both. And see.
有一个更好的解决方法。
Yes. We can discuss again later. Huh? So the plan for the rest of the lecture is we have 4 lecture left, including this one. So 1.5 weeks we finish vector calculus, and then the other 0.5 we finish all the. Okay. So next. Okay, so next is the line integral. Okay, line integral. So for line integral, we have to start with a line, okay, or a curve. We start with a line or a curve. Okay, so this curve is parameterized by E. Okay, so you will see why we want to parameterize the curve. Okay, so let me draw some picture for you. Oh, that time Tiansen went to my max lecture. He already learned this stuff. Let Tiansen. Let's okay. So your function, right? Okay, so if you want to integrate over this function, it's easy, right? Then you just do integration from a to b of f dx. Okay, but let's say this line here. Okay, so this line here, I put it into R3. Okay, I put it into R3. So maybe like this. Okay, so maybe let's draw it down. So how you integrate over a function over this line? How you describe all the points using 2 coordinates? Is it possible? 因为 the two 可以看到。So how? I mean, is it possible? How to integrate something like xy to AB, for example? Is this possible? Of d what then? Dx? E of the line? Right. So how we make sense of this? Double integral. Remember double integral? No, double integral will get 0 on this thing. Because this is not a box. Only box have positive volume. But if you reduce the box to the boundary, there's nothing on it. Okay, so how do we do this? So how we do this is using parametric curve. Okay, so meaning we can just use one variable to describe my path. Okay, I use one variable to describe my path. Okay, so I make it into one variable. So what's this? Okay, so remember last time what I said? So we have a parametric curve. We have R to R2 or R3. Okay, how the real line sit on this curve. Okay, and then we try to integrate this inside R3. Okay, can you imagine or not? Okay, can you imagine? Okay, continue first. Yeah. So first we have this curve. Okay, we use one variable to describe it. Okay, it is a line. We can use one variable to describe it. So we just use t, the time variable. And then what do we mean by integrating function along the C? Okay, what we mean is we cut off the C here. Okay, we cut it into intervals. Okay, and then cut it as small as possible so that this secant here will approximate the curve. Okay, so we cut it with more and more points to approximate the curve, right? So we take limit to infinity because we take more and more points. And then we sum up all these curves. But the line integral of f along C is we put weight of f on the C. So you can think of it, this C, this line here have some weight. Have some weight. So what are you integrating over? So the picture in your mind should be something like this. So you are integrating over the area of a curtain or a fence, or we call curtain or a fence. Okay, so you first start with a curve in the domain. Okay, and then along this curve, along this point, you have function. You define function on it. Okay, so if you input the point into the function gives you a number, right? Okay, that number is the weight. So the weight of every point. Okay, so you multiply the weight on the length of your curve, so you get the area of this shape here, or the curtain. Okay, we call it a fence or a curtain. Make sense? Okay, so this is a definition of line integral, but how do we actually compute it? Do you want to really take the sum? Do you really want to take the limit? Okay, so these are hard. There are convergence problems going on here. So the theorem is you can compute the line integral just using the formula here. Okay, remember what's the formula here? Do you remember what's the formula here or not? Do you relate to? Can you relate to what have you learned? The arc length, okay, the length of the curve, but there's an extra weight function here, f. Okay, so if your f is just 1, right? So if your weight is just 1, what are you computing is just the length of the curve. But now every point on your curve carry a weight. Okay, so you need to multiply by the function fxy. Make sense? Remember, this thing looks like a Pythagoras theorem here. So if you take limit to 0, so you get all the. Okay. And yeah. Okay. But first you need to make sense of this formula first. Okay. So you have an arc length and then multiply by the weight at each point, which is given by the function. Okay. If the function is just 1, then you are just computing the length. Okay. So far, okay or not? Okay. So let's look at example. So try evaluate the function 2 plus x squared y integrating on the line C. Okay, what is C here? So C here is determined by the parametric equation x equals to cos t, y equals to sine t. You should be very familiar to this parametric curve by now, right? This is the first slide we do. Okay, what's this curve? Circle, okay? But this circle is restrict from 0 to 2 pi only. Okay, so this is only the positive semicircle. Okay. But also note that we have different parameterization, okay, using the xy coordinate. So first is the polar. So this is the polar coordinate. Okay, so this is the polar coordinate. Yeah. So this is the polar coordinate. The bottom one is the rectangular coordinate. Okay, so both of this describe the semicircle. And we will try and integrate over these two numbers here. Okay. Do you know what's the difference between these two parameterization? You know what's the difference? Huh? One is t, one is x. So what does t and x represent here? Huh? What does t and x represent here? Huh? Yeah, yeah, sure. They both draw a circle, but what these parameters represent? So can you see that the range of t and x is different? Okay, so what do they represent? Sure, they are independent variable, but what's the physical meaning? Huh? Sure, I mean this is the range of the domain is different, but why? Why? Why we pick this? Why not I pick pi to 2 pi? Positive semicircle, okay? Because this is the time, okay? So this is the time on the polar coordinate, okay? At the bottom here, what is this? This is the coordinate of x, okay? So you tell me what point on x, I get what y, right? Okay. How about t? T is the angle, right? Angle on the polar coordinate, okay? So you are looking at this direction. Okay. Different angle, you have different. Make sense or not? Okay, so one is give a x axis, give a y like this, and then the other is you give an angle, you give me a point. Okay, okay. So we'll see that these two actually compute to the same thing. Okay, so let's look at the first one. So let's start with the first parameterization. So line integral. So how to compute line integral? First, you need to get a parameterized curve. Why do you want to get a parameterized curve? Because you want the integral to have only just one variable to integrate over. Make sense? Because my curve now living in R2, R3. Okay, you cannot write down all the coordinates anymore. So you need to make it easier using one variable. Okay, so see here. Our equation is x equals to cos t, y equals to sine t for t in between 0 and pi. Okay, so this is a parameterization. So we want to compute the line integral of C. So what's the formula of line integral here? integrate from 0 to pi, okay, fxt, yt, okay, so what's the function become in this case? 2 plus cos t squared y is sine t. Multiply by what? Okay, multiply by the change in the arc length. So change in arc length is what? X prime t squared plus yt squared. Okay, so now we need to compute what is x prime t and y prime t. Okay, x prime t is negative sine t, y prime t is cos t. Okay, so you get minus sine t squared plus cos t squared, and then dt. So you need to check whether all these make sense or not. See, function in t, okay, and then another function in t, integrate over t. Okay, so this whole thing should make sense. You don't, and then you integrate over the range in t. Okay, so every time when you write down the integral, right, make sure you check whether it is integrating over the right variable or not. Okay. Okay. Yeah. Okay, so what's this integral become? Sine t squared plus cos t squared is just 1, square root 1 is 1. Okay. So at the end, you just get 2 plus cos squared t sine t dt. So how to integrate this? You can use substitution. Okay, substitution maybe faster. Yeah, use substitution maybe faster. You also, maybe you can try double angle, but double angle, I think you might reach integration by part. So you could take u equals to cos t, du equals to minus sine t, dt. Okay. Yeah. So what happened to our integral here? So this integral here will just become integral of u squared minus du, which is minus u cubed over 3. Yeah. Okay, which is just cos cube over 3 plus sec. Okay. Okay, so all together, what do you get? So you can integrate 2 first, and then integrate cos square t sine t, which we get minus cos cube t over 3. Okay, so we get 2 pi plus 1 over 3 minus 1 over 3, and we get 2 pi plus 2 over 3. Okay, can follow? Can follow, no? Can follow? Okay. Any question? No? Question or not? Any question from the right? Yeah. Okay, let's try another parameterization. Okay, try another method. See we get the same answer. No? C2, C1 as well. Okay. So how do we parameterize? we take x, depend on x. There's a problem here. How about we change our variable to t also? Okay, we change our variable to c. Xt over t equal to t, and xy. Okay, let me write down something first. So xx over x, and then yx over, what is this? Square root 1 minus x squared, for x in between, minus 1 and 1. Okay, so I think this notation a bit confusing. Okay, so I want to change the parameter to t as well. Okay, so I change it to t. Xt equals to t, yt equals to square root 1 minus t squared. And t is in between, minus 1 and 1. Okay, can you realize that these two actually are the same thing? These two actually are the same thing. Okay, what I mean here is this 2x here, okay, the first x and second x is really a different x. Okay, so the first x here is just a name. Okay, it's just the name of the function. But the second x here is the parameter. Okay, similarly to the third x here. Okay, so there are 3x here, these 3x are different. Okay. Can buy this or not? Yeah. All right, so next. So if I change to this parameterization, right, what am I doing? Let's copy down this function first. So what am I doing? So I need to replace my function with dt again, okay, from -1 to 1 of 2 times x in terms of t squared, y in terms of t, okay, multiplied by what? By square root x prime t squared plus y prime t squared. Okay, so similarly, we need to compute what is x prime t and y prime t. So x prime t is just 1, y prime t is just minus t over square root, not square root anymore. It's a square root. No way. 3 over 2. Oh yeah, okay. So over already become a minus half. So over 1 minus t squared. Okay. So can you notice that your s prime t and y prime t is different from the previous one already? Because we are using a different parameterized curve here. Okay. Can you see that they are already different? See, they are different here. Their derivative is different. Okay, because you start with a, not because, but I mean they are different. Sometimes you start with a different thing, maybe you end up with the same thing. Okay. Okay. So next, what are these? So integrate from -1 to 1 of 2 plus x squared, sorry, t squared times square root 1 minus t squared. Okay, square root of 1 squared plus y squared. So t squared over 1 minus dt. So it might seem very complicated at first, but you can reduce the square root to just what? Just square root 1 over 1 minus x squared. Sorry, t squared dt. Okay. Okay. Okay, next, what happened here? So you can split out the integral similar to what we did last time. So one of them is 2 over square root 1 minus x squared. The other is just x squared. Wait, what am I doing? Oh, t. dt. Okay. So the second integral is easier. How about the first one? Yeah, you can move the constant out and then you integrate 1 over square root 1 minus x squared.
I believe you do a lot of calculus one, right? So what's this? What's the integral? What's the integral? Sine. Yeah, sine. Inverse of sine. Yeah, you get inverse of sine. You can use the trigo integral here. So we will skip that. So you can try it. The trigo integral. Okay. Don't. Why I keep asking this kind of question?
然后 probability 给我们的创建大，非常的大。教的东西、练习的东西跟这种东西三个东西。
Learn first. Later we can decide.
所以我说的更加
Your life is not for exam, you know. That's true also.
人家没有考试哦。
Money is not important, but you must have money. Okay. Okay. Next, what is what? So what's this? So you get 2 times pi over 2 plus pi over 2 plus 1 over 3 plus 1 over 3. Okay, so this is also 2 pi plus 2 over 3. Okay, so what's the moral of the story here? What's the moral of the story? Why you have a different story from me? So what's the story? What's the moral of the story here? What? Don't do second time. Why catch different main point? What's the moral of the story here? Qingrong, what's the moral of the story? Yeah. So you start with a different parameterized curve, you get a different answer. So no matter how you parameterize your curve, you should get the same answer. Okay? Yeah. You can have different way to parameterize your curve, but you will always get the same answer. So the line integral doesn't depend on the parameter, parameter function. Sorry? No, it's the same part, but you walk different way. Still the same. It's the same path. It's still the semicircle. It's still the semicircle. Just you see from different perspective. Yeah. Okay. Okay, next. Try evaluate this two. This line integral here. But this line integral here consists of 2 parts. Okay, C1 and C2. One is following y equals to x squared from 0, 0 to 1, 1. And then the other is following a vertical line C2 from 1, 1 to 1, 2. So you should also note that this line integral here is also additive. Okay, so you can split out into union of line. Okay, integral is linear. Integral operation is linear. So you can split out your integral into. So let me write down what I say. So this line integral here can split out into integral of C1 and C2 and add them up. Okay, so you can split into C1 and C2, where C is C1 union C2. Okay. So when I say union, right, they only connect on the boundary. They only connect on the boundary. You don't tell me C1 up to here, C2 up to here, then you will have a non-empty intersection here. You will calculate more stuff. They only intersect at the boundary, okay, at one point. Because above one point, the integral is 0. And so let me add a remark here. So connect at boundary. And so this is similar to what we have discussed before, actually. So this means that the integral operator is linear. Okay, you can split it up. Linear on the set. Yeah. Also linear on function. We already see it. Okay. Yeah. So we want to compute these two integral here, C1 and C2. So this is a curve in R2, right? Okay, curve in R2. So we need to parameterize it using one variable. Okay, how do we parameterize it? So C1 is what? Okay, sure. I mean, what's the parametric equation for xt and yt? Okay, x equals to t, yt equals to t squared. Okay, good. So t is going from 0 to 1. Okay. How about C2? Xt equals to 1, yt equals to 1 plus t. No way. No, right? You want to use, because you want to change your t to 1 to 2. Is it the reason? T from 0 to 1. So I mean, the one that I will pick is like t is yt is t, and then t is going from 1 to 2. Unless you change your domain. Okay, unless you change your domain. But as long as if they define the same, so as long as they define the same curve is fine, right? Because just now we already said that it doesn't depend on parameter. Okay, C2, you can see that, you see, the x component is keep the same, x1, but how you change in y, okay, how you change in y, you take all the t from 1 to 2, okay, so yt equals t. Okay, okay, so what are the ingredient you need? You need the first derivative as well, y prime t and x prime t. Okay, so for C1, x prime t is 1, y prime t is 2t. For C2, y prime x prime t is 0, y prime t is 1. Okay. So maybe to avoid confusion, let's give x the x and y in C1 for by x1, y1, and then for C2 we give x2, y2. Okay. I give you 3 minutes, see if you can assemble this thing together to compute line integral. Let's try. Here is the place for you to make mistake. If you go out to the world, if you make mistake, then people will look down on you. Okay, so if you want to make mistake now. And try see if you can compose everything together to compute something. Who just came just now? 杭州 just came. 高启胜. So
Okay. Where? Okay. Give you a bit more time. Down. Are you calculating? Why not? Almost done. Okay, let's go through together. Okay. So first, what's the range? So first range, we go from 0 to 1. Okay, we need to replace our x with xt. And then multiply with the extra arc length factor here. Okay, x prime t squared plus y prime t squared. Okay, times dt. Similarly, on the other integral, we have 1 to 2, integrate from 1 to 2, or 2 times xt square root the arc length factor. Okay. And then we need to input xt in for the c1. C1 here we get t. Okay. And then what's the arc length factor here? It's just 1 squared plus 2t squared, I believe. Plus integrate from 1 to 2, 2 times 1 over square root 0 plus 1 squared dt. Okay. So all together here we get t times 1 plus 4t squared dt plus integrate from 1 to 2, 2 times dt. Right? So how to integrate the first integral here? Okay. So what we do here is also integration by substitution. Okay, you can use u equals to 1 plus 4t squared. So du equals to 8t dt. And 8t dt. Sorry? What? Where? First one? Oh, I mean, yeah, we need a 2. So 2t, 2t. Okay? Yes, correct. Okay. Okay, so if I do the substitution, integration by substitution, what do I get? I get square root from 1 to 5, okay, of square root u du over 4. And the other one, I just do it 2t, integrating from 1 to 2. Right? Right. So when u equals to 0, sorry, when t equals 0, u equals to 1. T equals to 1, u equals to 5. Okay. So all together, what do we have? So we have 1 over 4 of u to the 3 over 2 over 3 over 2 from 1 to 5 plus 4 minus 1 is 3. Okay, so here we got 1 over 6 of 5 square root 5 minus 1 plus 3. Correct or not? Plus 3 or plus 4? 2 to 4 minus 1. Oh, yeah, okay, sorry. Yeah, 2. Okay. What else?
Yes.
Correct. So what's the final answer? What's the final answer? The final answer is equals to 1 over 6, 5 square root 5 plus 11. Okay? Okay. Okay. There's actually another method to compute the straight line here. Yeah, another straight line to compute this straight line here. Okay. So do you notice that this is an area? So let me write down. So do you notice that? Let me write somewhere right here. So do you notice that this integral of 2x dx is an area of rectangle with base, this one, and height 2. Right, so this is just 2 times 1. Okay, so you should be able to see this to make sure you know the concept. Okay, so what happened to this line here? What is the weight for the line here? 1, right? Sorry, not 1, it's 2. 2x. Okay, here all the x is 1. So every point here carry a 2. Make sense? Yeah, so fxy here I refer to 2x. The function you integrate over, okay? But over this line, x is always 1. Okay, so all these points carry a weight 2. Okay, so you see, if you integrate under this curve here, you just get the area of a rectangle. 2 times the base, which is 1. You understand or not? You understand? Yeah. So you should imagine the third axis here. Okay, third axis z. Okay, so the height here is 2. Okay, so the height here is 2. So here is 2. Okay, height. The height, the third dimension. You have a height. Yeah. You have a height. Yeah. Okay, so third dimension. Okay, so this is a rectangle. Okay, so with a height 2 and a length 1. Make sense? Okay, okay. 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 Next. Okay, next, we have also line integral with respect to x and y. But why we define this, maybe later will make more sense. Okay, when we do a vector integral. Okay, so just now we put, what do we do? Just now we put this integral against our the length of whole curve dx. But now we just put a certain function along s or along y. Okay, so if it is along x, along y, you can see that the factor of, let me write down, the factor of the arc length, okay, one of them reduced to 0. You notice that? See here. One of them reduced to 0. Okay, so for example, if you want to look at what's the dx change, so the dy change, you ignore it, it becomes 0. Okay, so square root x prime t squared becomes just x prime. Okay, and then similarly, if you just look at what's the change in y, you disregard the x direction, you make the x prime become 0. and then square root y prime square just become y prime t. Okay. Actually, this one, right, this is really similar to the integration by substitution. Okay, you substitute your x by t. Okay, you drop out a contribution from the derivative of x prime t. Correct or not? Remember just now what we do here, you see? When we do the substitution, integration by substitution, okay, you substitute your t, okay, by u, okay, you write it as a new variable. Then you have an extra contribution here, okay, u prime t. Okay, so this is really similar. Okay, let's see how this works. Okay, let's see how this works. So we want to integrate the following function, y squared in the direction of x, x in the direction of y, okay? And you are given two lines. One is a line segment. So what's a what line segment? It's a straight line, okay? Straight line, and then there's an end point and a starting point. So the starting point here is -5, -3. The end point here is 0, 2. And the other curve is C2. Okay, C2, what is C2? The arc of a parabola, which is x equals to 4 minus y squared. Also from the starting point -5, -3 to 0, 2. So what's the similarity between these two paths? Okay, they start at the same point, they end at the same point. Okay. All right. So let's do the computation. So how do we parameterize C1? How to get line segment? Okay. Line equation. Okay, so which line equation you want to use? What have you learned before? Vector function, huh? You need a point and a vector. Okay, so what's the point? What's the vector? What's the point? What's the vector? I think we did this in midterm, right? Midterm exam. Okay, you need a point, you need a direction vector. So what's the point? What's the direction vector? Point is -5, -3, okay, because you want to start from there. Sure. Direction vector, 5, 5. So how do you compute that? So you take 0, 2 minus -5, -3. Okay, so you get 5, 5. Okay, so the line equation is equals to points plus VT, right? Okay, so we call this P, we call this V. P is -5 -3. Okay. V is 5, 5. Okay, but what's the T? T is going from where to where? 0 to 1. Okay, so T is going from 0 to 1. So you need to check whether this is true or not. Is this true? So when T equals to 0, we start with -5, -3. Okay. When T is 1, okay, what's the addition of this? We just get 0 and 2. So which is the end? So this is the line connecting the starting point -5, -3 and the end point 0, 2. Okay or not? This is revising what we did before. Yeah. So you see, this is not parametric equation yet, right? Okay. So last time we learned this is a vector equation. So we need to write it as a parametric equation because parametric equation is what we need for our computation. So that's why last time you learned, you need to know how to write as a parametric equation. You also need to know how to write a vector equation. Okay, so these two have some advantage when we do some different calculation. So what's the parametric equation here? St equals to -5 plus 5t. Okay, yt equals to -3 plus 5t. Okay, for t in between 0 and 1. Sure. Okay, good. And then yeah, so we want to have two direction, right? So the two direction require x prime t and y prime t. So what's x prime t? Just 5. Y prime t is also just 5. Okay. Okay, so let's go to the real business here. So we want to integrate c1, okay, of what? Of y squared dx plus x dy. Okay, so what's the first integral become? So we need to replace the x and y coordinate using the parametric equation. So the domain becomes 0 to 1 of y in terms of t, okay? And then multiply by x prime t dt plus integrate of from 0 to 1 xt of y prime t dt. Correct or not? This is the formula we have just now. Can you see it? So when we integrate with respect to x, there's a factor x prime t. When we integrate with respect to y, there's a factor y prime t. Yeah. Okay. Yeah. So let's continue. So what is yt? Yt is minus 3 plus 5t. And what is x prime t? It's just 5 dt. And then keep going. Integrate from 0 to 1. Xt is minus 5 plus 5t. Y prime t is 5 dt. Okay. Yeah, so what's this all together? Yeah. Y squared t. Y squared t. Okay, sorry, y squared t. Good. So we have a square here. Okay, so what are these? 5 times. Oh, it seems like I skipped step here. So maybe you try and check whether this is 4 minus 25t plus 25t squared or not. Okay, try expand the square and then see if you combine to this function here. And then these are just polynomials, so should be easier to integrate here. Zero to 1. And then altogether you will get 5 times minus 1 is 6 equals to minus 5 is 6. Check if you get the same answer. Oh, for cheating. Are you computing? Huh? Can follow or cannot follow? Follow? Okay. Try and compute. Later go back also no time compute. Huh? Is it? Yeah. Don't spend double times to one word. Right? Don't spend double time and do one word only. Yeah, this is what we learned in school. So, right. 事半功倍and 事倍功半. Yeah. Check. Huh? What? Anything wrong? Anything wrong? I think I checked this answer before, should be correct. OK 啊。Yeah, combine because they have the same domain as combine. Okay. Okay. How homing? The confusion. Okay, there's another way to describe this line, right? You know what's the other way to describe this line here? What's the other way? There's another way to describe this line. Line equation, also line equation. Y minus yi over x minus xi equals to y2 minus y1 over x2 minus x1. Okay. Yeah. Yeah. I mean, for myself, this one may be more intuitive for me, right? Because this is the first thing we learn when we see line. Okay. So if you compute this, right, the line we have is y equals to x plus 2. Okay. And so to get the parametric equation here, we have xt equals to t and yt equals to t plus 2. But this t here has different range. Okay, what should be the range of this t here? T is going from where to where? T is going from -5 to 0. Okay, yeah. So you can if you compute everything using this parametric equation here, you also get the same answer. Okay, you can check that you also get the same answer. Yeah. Okay. You want to try? You can convince yourself. Okay. Yeah. So if you try this parametric equation, you also get the same answer, 5 over 6. Negative 5 over 6, right? Okay. Any question on that? We haven't do C2 yet, right? Maybe we take a break and then we come back and do C2. Yeah, we still have C2. Yeah, let's take a break until 10, 10:05.
这个玩意都可以玩儿嘞。
I mean, you can see it like this one also can. You can see it like this.
This integral can share with who one.
Because this is the because this is the definition of line integral. Because this c here, this c here represent xy direction. So it can be defined like this.
Weird, so weird one.
Not weird because remember just now we said that this curve actually has x and y component. Yeah. Yeah. So this integrand here doesn't mean only have x direction or doesn't mean only have y direction. If this integral here only represent x direction, then you cannot put outside because doesn't have y component.
Oh.
But this one actually represent everything. Okay, so when we split it into t, then
They will go to stay a separate.
then only this integral here, meaning I only take integration for the t variable on this side. Yeah. 有
我这个背离区间是要换成 t 的是吗？
啊，
它是背离区间要换成 t 的。
对，换成一个 variable。因为这里的话是一个线，那个线是活在 R2 里，你就不能够每一个点你都去描述它，对，很难描述。但是呢，你可以用一个 parameter 去描述两个。
然后就是最后的话就是一个上传，就是那种revision
会上传，我已经上传了，
questions，
我已经上传了。
就是那种就是期末考试那所有 chapter 的 revision question，不是一张。
哦，没有了，就是那些，就是那些，就是那些。
尤其是我们 calculus one 的时候，就是
哦，有啊，
就把所有的那个期末考试会可能考到就是那个 calculus 的所有的 revision question 都就是上传。
OK 啊，
我们没有就是不会 calculus revision question。
没有，就只有那些。如果你还想做题的话，就课本哦。好吗？没有东西是。
你那堂课还有什么课？
我没有考。
有一点就是，对啊，是的，对。
不要，现在不要，
现在不要，
这么有搞不？
不要，不，那哪里搞？我会得买，我买个飞的了，别买个飞的，飞的我是类似，就是你在美国，我在买个飞的，我买个飞的，谁买你打球人买个飞的，怎么样买个飞的啊？怎么买？女的啊，女的，我们就讲飞的才买哟，我才就我吃，
你吃啊，你吃。
你要吧
OK。
然后被缴费啊，敢吃还可以。多耶穌佢哋繳費啊，真係 Why are you so fat？
我又是一个 meme
啊，
又是一个 meme。
没有啊，只是讲嘛。你是不是每次会托梦给你们呢？会吗？对现在的概念有讲会托梦给你发生什么事情啊？没有咩？那边来有了，就是讲他们的概念是什么？就是说
看到意象，
就是发梦的时候看到，所以你你的好朋友红一线，然后记得有托梦过你，
不懂。
就是你觉得
看到
周报没有看到，你不可能看到他的人啊，肯定
应该是你这次啊。
哦，你没有戴眼镜睡觉啊？要戴眼镜睡觉，你才可以看到更多的事情。也不看。
所以你们等下有 presentation 吗？什么呢？
就是
那个你是什么的？245。对。
哎呀，真超
全部人加爱睡。
累呀，
什么？忙什么？忙什么？忙什么？
一定不忙。他忙个啥？我一个跑个有一个小龙虾，然后把那小龙虾下到喷洗。哦，那你还记得这层啊？你那么洗个几次的嘞？我这不会是回家看了吗？啊？对啊，因为这演的飞机是你的同学，就那个同学，对，有个飞机，我是不是他以前在你们中教过书？他教过你？他没教过，他教我隔壁班。啊，他走了啊，走了，快点啊，快点走。没有，不是我讲他不在啊，对对对，没朋友啊，音乐教授。 老公压抑的。对嘛？如果你参加节目，就是以前之前就已经做到这个。他对，这是我。
这是来定。
Hello, testing. Okay. So let's continue with C2. Okay, what is C2? Okay, so what is C2? Okay, what's the parametric equation for C2? To 4 minus t squared. Okay, and then yt follow t. Okay, because you can see that x is equal to 4 minus y squared, and then y just follow y. So what's the range of t? T is going from where to where? Or the y is going from where to where? Okay, so t is going from where to where? What's the y coordinate? From where to where? What's the y coordinate? Huh? Yeah, I mean, say do you know? Where's the y coordinate? So t is going from -3 to 2. All right. Okay. So you want to compute a line integral, you still need the first derivative for x and y. So sorry. What? What do you mean by t to t? Oh, t to 2. Okay. So x prime t is -2t. Y prime t is 1. Okay. Hey, don't play. Don't play. Okay. So integrate for C2 on y squared dx plus x dy. Okay. Okay. So what do you do? Okay, you need to change all the xy coordinate to t. Okay. So our t is ranging from -3 to 2. And then we need to replace our y by yt. Okay, yt squared. And then dx become x prime t dt. Plus x is what? 4 minus, sorry. X become xt of d dy prime t dy dt. Okay, so just now, right? Just now, Hongming, I think Hongming asked a very good question here. So you see, I write integral of a curve. Okay, but why this integral here include all the dx and dy? Okay, why not I put another integral here? Okay, why? You can, but I mean, this also makes sense actually. Okay, so this also makes sense. So integrate of C2 of the whole thing also makes sense. So why? Why does it make sense here? Because this integral here is going over the curve, but the curve go through x and y. Okay, so this makes sense here. Okay, but let's say the right one. Okay, this integral here only cover t. Okay, if you change to another variable, then you cannot put them together. Okay, so here the integral here only works on t. Okay, but the integral on the line integral work for x and yeah. Okay, so you need to make sure you know what are you integrating over. Okay. Okay, next. So y t squared is what? yt squared in this case is t squared. Y prime t is x prime t is 4 minus t squared. dt plus okay, so let's move this up. So xt is 4 minus t squared. Y prime t is 1. Correct or not? X prime t. So what do I miss out? Okay, so this one become minus 2t. Correct or not? Yeah, okay, good. So altogether, what do we get? We get 4 minus t squared minus 2t cubed. Okay, so these are just polynomial. So just get 4t minus t cubed over 3 minus t over 4 over minus 3 to 2. Okay, so altogether you get 245 over 6. Okay, you should get 245 over 6. Okay, so does everyone got this answer yet? Verify this answer. Check that you got this answer. Okay, Martin got this answer. Okay. Yeah. Yes. Okay. Okay, so is 245 over 6 equal to minus 5 over 6 or not? 245 over 6, is it equal to minus 5 over 6 or not? Okay. So it's not equal, right? Okay. So you can see. So although we integrate from the same starting point to the same end point, okay, if we use different path, they get different value. Okay, so they get different value. Okay. So although your starting point is the same, your goal is the same, but if you use different paths, you might get different value. Okay. Yeah. So it depends on the path you take. No. I mean, this integral will depend on the path you take, not just the endpoint. Huh? What? I already tell you the can be different. Yeah. Depend on the path you take. Okay, it doesn't depend on the endpoint and the starting point. What does this number represent? So, like what we said just now, if the function is always positive, then it represents the area above. Negative go on the difference. So remember the volume stuff. So if they are positive, negative, so they add up together, which one is bigger? The difference is negative in that case, in this case, if it is negative. If the difference is positive, then positive. Remember or not? Forgot already. Remember we have a volume example. We compute to 0. Remember or not? So remember the volume example last time? Yeah, remember the volume last time we compute to 0, but there's volume above positive the z equals 0 plane and below z equals 0 plane. And then the difference of them is the integral that we are computing. The difference. The difference of area above positive and below negative. Okay. Okay. Yeah, you see, there's a criteria here. So if the function is always positive, only represent the area. Okay. Otherwise, it might go under. Then you have the orientation change. Okay, so let's look at this now. So in general, right? Okay, in general, okay, positive semicircle. You can go from the left to right.
Hello, for business. Okay, so positive semicircle, right? You can go from the left to right. You also can go from the right to left. Okay. So if you swap this direction, what happened to your integral? Okay. So this is the criteria here. So if you take different orientation, okay, then the integral will differ by a negative. Okay. So if you integrate over negative orientation, is equal to the negative of the original orientation. Okay. Yeah. Okay, so quite easy. Yeah. Yeah. Different direction will incur a negative sign. Okay, easy to follow. Okay, so meaning if I integrate, I mean, this is quite easy to see or not. So let me see. So you can see if I integrate, if I swap the integration from 1 to 0, not from 0 to 1, we just get minus of 0 to 1, right? So we swap the integral by a minus. Okay, so this applied to the arbitrary curve. Okay, arbitrary curve. Okay, next is a line in 3D space. So we not only can do 2D, we also can do 3D. So 3D here, we just add an extra z prime factor. Okay, so you can do n space. Okay, nd also again. Okay, nd. You need to add until sn prime. Okay, should we do this example or skip? Yes. Okay. Because this is just an extra factor. Huh? Sometimes it gives you the parametric equation. Sometimes you need to construct the yeah, here you already given. Okay, maybe this one is easier. Maybe do the next one. Okay, this one is given already. So next do this one. Okay, let's do this one. So you have this function here, y dx, z dy, x dx, dz. Okay, consists of the line segment C1 from 2, 0, 0 to 3, 4, 5, and a vertical line segment. So these are just line segment, right? Okay, so line segment are relatively easier. Okay, so because this is already 3D, right? So the y minus y1, x1 over x1 doesn't work anymore because this is 3D. Okay, so this have to rely on the point plus a direction vector times t. Okay, use that formula here. So similarly as just now, you see that this curve here is the union of two straight line, two lines. Okay, two straight lines. So you can split at the boundary. Okay, split at the boundary. So let's do what is C1 first. Let's parameterize C1. So what's the ingredient you need to find the equation of line? Point and direction vector. Okay, direction vector. Direction vector. So what point you want to take? When you take the starting point, 2, 0, 0. What's the direction vector? Okay, 1, 4, 5. How do you get that? You take the end point minus the starting point. And then you will get 1, 4, 5. Okay, so the line equation here is P plus VT. Okay, P is 2, 0, 0. V is 1, 4, 5 times T. T go from where to where? Okay, 0 to 1. So this is the tailor-made for this line. So 0 at the starting point, 1 at the end point. Okay, so this is tailor-made. Okay, so but this is a vector equation, right? This is a vector equation. So we want a parametric equation. So what's the parametric equation here? Xt equals to 2 plus t, good. Yt equals to 4t, good. Zt equals to 5t. Okay.
Yeah. And then what's their derivative? X prime t is 1, y prime t is 4, z prime t is 5. So you can see that this derivative is actually the direction vector, right? 1, 4, 5. Okay, so that's the relation here. Okay, so this is C1. We have done C1. How about C2? Yeah, how about C2? How to describe this vertical line? This C2 should be easier. This C2 should be easier. You can, but you will reduce to something trivial. Trivial is not important. Yeah, something like that. Something easy. Something easy. Okay, so can you observe something or not? This is a vertical line. Vertical line, what does it mean? Only z is changing. Okay, only z is changing. So x is what? X is always 3. Y is always 4. Z is changing with t. Changing from where to where? 0 to 5. Okay. So Chiesen, you also can use this method, point and direction vector. Okay. So you can use point 3, 4, 5. Okay. Direction vector. What is direction vector? 0, 0 minus 5. Okay. If you write down the line equation here and get the parametric equation here, is exactly what we have here. Right? 3, 4, 0 plus. Okay. Yes, your z is 5t, correct? Because why? Because why? Because your t is going from 0 to 1, but you need to get the 5. So you scale your function by 5. Yeah, it's the same. Yeah. It's the same line. But just now we see that different parameter give you the same integral. Yeah, yeah, it's the same. Yeah. 李一章啊. Okay. Okay, so yeah, so in this case here, you can see that this is a vertical line, right? No change in x and y. Okay, so similarly, you will see that x prime t is 0, y prime t is 0. And in the z direction, you have 1. Okay. So now it's the job to put everything together. Yeah, put everything together. So your integral is from C1 to C2. Okay. Sure. C1 to C2. Size. That what? That what? Huh? Oh, yeah. I mean, wait. That's 5t. Yeah. Okay. Yeah, sure. Okay, let's address the question again. So if you use the point and direction, right, you get xt equals to. Okay. Let's write down the line equation. So L2, maybe this one L1. So L2 is let me write down 3, 4, 5 plus, so 0, 0 minus 1t, right? This is what you get, right? Okay, so t is going from 0 to 1. Okay, so I claim that these two give the same line, right? These two give the same line. Okay, when t equals to 0, you get 3, 4, 5. Okay. Oh, this direction is different, is it? Wait. Oh, I know. Okay, so this direction is different, right? Okay, so actually we need to change the direction of t if we want to do the integral. Okay, so we need to change this direction. Change the direction. Although they are the same inequality, but we just denote that we change the direction. Okay, we integrate from 5 to 0 instead. Okay, instead of 0 to 5. Huh? Wait, what? So one by one. Who say first? Coming first. 我这样客气了。Okay. Then, oh, you mean for C2 has? You also can use 5 minus t. You also can use t, but if you use t, then you turn your domain. If you use 5 minus t, then you don't need to turn your domain. Yeah. Huh? Okay. Okay, there. What? 0 to what? Say again. Okay, so Buntat suggesting you can use this one. Okay, you can use this. Buntat say use this 5 minus t for t go between 0 and 5. 0 and 5, yeah, correct. Wait, one by one. So here, this one is my method. First is my method. Second is this line method. Okay, when can just now let's see. Yeah. Direction for which one? For L2, let me think. Next 5 or okay, yeah. Sorry, this one is -5. Yeah, right. Okay. And then the third method is this Buntat one. Okay. So far, okay here or not? Here, okay. Which one? Which one? Which one? The third one, the first one, or the second one? L2, L2, how to compute L2? You need, huh? Yeah, I mean, just calculate wrong. Calculate wrong. Huh? No more question, huh? Okay, yeah. Wrong number, just wrong number. I mean, you check, right? So you put t equals 0. Do you get 3, 4, 5 or not? Okay. You put 1. Do you get 3, 4, 0 or not? You put 1. Do you get 3, 4, 0? Then you put 1. Put 1. Put 1, you get 3, 4. 5 minus 5, you get 0. Okay. Yeah. So there are 3 methods here. Okay. And any one of them give the same answer. Which one? Which one? Okay. This one also 5 minus 5t, huh? Okay. Yeah. Yeah. So similarly, you also check. You put t equals 0, what do you get? Put t equals to 5, what do you get? Put. Wait, you guys, be careful on what domain I use here. Okay, be careful on what domain I use here. Here I use 0 to 5. Okay. If you want what? If you want 5t, then I can do the fourth one. Wait, so you can use this as well. Okay. So the key part here is you need to make sure you know what's the domain you use. Okay, the domain you use, and then this will determine what kind of parametric equation you use. Okay, anything will work as long as you give the same endpoint. Okay, the same endpoint will work. Okay or not? Okay, 4 of these explain the same line. You should check. Okay or not? Okay. Okay. So to check that they give the same orientation, you need to check the order of the orientation of your domain. Okay. I mean, the hardest part for integral question, right, is to determine the domain. Okay, this is the hardest part. Okay. To integrate is just a normal integration, usually. Okay. Okay. Any more question or not? Any more question? So the most direct check is you plug in the starting point and end point into your equation. See if you get the same endpoint or not. Okay, this is the most direct check. Okay. Okay. Okay, so we will stick to the first example here. I use the red one. Okay, we use the red convention. Okay, we use the red convention. Okay, so this integral here split into C1 and C2. X dz. Okay, so when you split into two integral here, okay, so we need to replace our domain, okay, 0 to 1 for C1. C2 is going from 5 to 0. Okay, so if I use my convention, I need to integrate from 5 to 0 because it's opposite. Okay, or you use the negative of the orientation also can. Yeah, negative of 0 to 5 also can. So you need to know what you are doing. Okay. Huh? But okay. So y dx is 4 times 0 times dt. Okay. Plus z is t times 1 times dt plus x is what? 3 times 0 times dt. Okay or not? C1. Yeah. Wait, this one is 1 or 2. Yeah, correct. Okay, so this one move it down. So this one move down. So this is a C2 one. So let's check what's C1. I mean, hey, I tell you, mistake is very precious. You know why? You know why? You know why? You know why? Let me tell you why. Let me tell you why. There's a reason one. There's a reason one. There's a reason one. In research, if you keep computing the right stuff, right, you don't know why you compute right one. Seriously, only through mistake, you will know, oh, this thing is very important. You know? Yeah. Instead, you can find the key. If you keep computing the right thing, you don't know why it's true. You really don't know. Seriously, you don't know why it's true. So mistake is very important. Okay. Okay. Continue. Okay, 0 to 1. Okay. 4t. Wait. Come back. Okay. So for C1, for C1, we have what is y? Y is 4t, and then what is x prime t is 1 dt. Plus what is z? Z is 5t, y prime t is 4 dt. Plus what is x? X is 2 plus t. Dz is what? 5 t. Sorry, 5 dt. Okay, so if you confuse what I'm doing, right? So let me write down something here. So here is yt on x prime t dt, and then here is zt on y prime t dt, and then the other end is x t times z prime t dt. Okay, so similarly at the back we also have these formula behind to check whether I use the right thing or not. Check one, cross check. Yeah. Okay. You can. Okay, so you can combine everything, right? So what can you do? So you could combine. So you could combine the 4t plus 20t plus 10 plus 5t dt. Okay, and then the other one is 5 to 0, 4 plus t plus 3 dt. Okay. Yeah, all together, what do you get? Yeah, all together, what do you get? 9.5. 9.5. Ooh. I didn't take some here. Okay, so one of them is 49 over 2. The other is minus 15. So all together is okay, yeah, this one finish. Okay, so here is 3. Okay.
只剩下3，只剩下3分。3。
Wait. Yeah, lo.
Y prime
Number 3 is wrong.
Y prime t 是0。
Wait. Let me see. Yeah, I substitute wrong. So here is 0. Okay. And then z prime t is 1. Okay, so here you got 3. Huh? Yeah. We use the number 2, number 1 one. So I get 19 over 2. 19 over 2, 19 over 2. Yeah, 19 over 2. 19 over 2. 49. 49. Okay. Okay 了。没有昨天。没有，我是早上。
今天早上回来。
昨天。
哇。
昨天跟 MAT 的人讨论到12点。
我说讨论没结束。
对，没有。Okay, so 19 over 2. Do you all get 19 over 2? Okay. Yours. You no. Same line, different of parameter equation, same answer. Different part might get different answer. Yes, different domain. Part as different domain already. So do you get the same line or not? The question is, all these 4 methods here, do they give the same line? If they give the same line, you are integrating over the same domain, then you get the same line integral. See what? 1, 2, 3, which one? Number 4, yeah? You get the same answer because the z prime here changed. Yeah, z prime here is different already.
Yeah, -5. So it's different from the z prime in 1. So you will get the same answer. Because the z prime already counted the changes. Ah. Same curve, different parameter equation, same answer. Because it's the same curve. Same curve, same answer. Different curve might be different answer. Yeah. That's a direction problem only. That's only a direction problem. Okay, so you get a negative on the orientation. Okay. Same curve might have orientation problem, but yours get the same absolute number, absolute value. You need to know how to do practically also, not just theory. Okay. Okay. Okay or not? No. Where? Yeah. Huh? Okay. Which part? This part? Wait. Ask here. Wait. Ask here. Yeah. What's the problem? Okay, so let me write down. So same curve. Okay. Same curve, same orientation. Okay, so let me write down here. So same curve, same orientation, different parameter equation, same line integral. Okay. Okay. Different curve might give different line integral. Okay. Can or not? So why do I compare these two? What is this two? Because why we compare these two? These two is because we have the same endpoint. Okay. Only comparable when they have the same endpoint. I mean, we have the same endpoint but have different curve. So let's say this is C1, this is C2. Okay. C1, C2 might get different number. Okay. But if you get C1 and then you parameterize it different way. Okay. Well, for example, this one I use X, this one I use T. Whatever you use, you still integrate over C1. It's still the same line. Make sense or not? Okay. Nothing abstract here. Nothing abstract here. Yeah. Right? Okay. If things get written down, then it should be clear. Between 2 points. Yeah. Yes. Okay. Case closed. Yeah. Okay. So continue the last concept of the day. Is work done? What is work done? Force time distance. Okay. So when you use apply force, right? I realize in your class, some of you very hardworking. Okay, very hardworking, but I don't see result from you. Why? Oh, wait. So why you don't get the same proportional from work done and result? Why? Because
You apply force, but there's no displacement. Okay, you apply in the wrong direction. Okay, so you need to check whether your method is correct or not. Okay. Yeah. Okay. So you see, if your displacement is 0, no matter how many force you put in, your work done is 0. Okay. The worst thing is displacement is negative. You apply positive force and then you get negative work done. Okay. So yeah. So you need to find. So you need to find the answer and check how to apply your force properly. Okay. Maybe you need to use the result to check or other thing. Okay. So you need to check. Okay. I don't know. Okay. So W equals to Fx. So in this case here, in the 3D direction, okay, so in why W equals to Fx? Because this is only one direction. Okay. So in your physics, there's only one direction. X is going one way. Okay, either positive, either negative. But in 3D space, right? Okay, you move this bottle in 3D. Or here is positive or not, or here is negative or not. We don't know. Okay, so we need to go through 3D space. Okay, so how to go through 3D space? We use dot product. Okay, because we dot two vectors together. Because your force gets split into 3D, and then your direction also split into 3D. So two vectors together, how to get a value? One way is dot product. Okay, use dot product. Okay, so how you compute work done in 3-dimensional space? You integrate the curve over the dot product. So first is the force function. Okay, force function. The other one is the change in your displacement, dr. Okay, F dot dr. Okay, so what is dr then? Okay, so what is dr? Okay, what is dr? So you can do the parameterized equation again. Okay, parameterize your curve. So you write everything in t. Okay, so you split out this r prime t again. Okay, split out this r prime t again. So what's r prime t is it in this case? This is actually the derivative of your vector function. So what's the derivative of your vector function? Yes, so no gradient. This is a unique vector. Okay, we call it a unique vector. Okay, we call it a unique vector. So repeat what? Repeat. So okay, so you got a line. Okay, so you got a line C. Okay, so let me write down. So you got a line C. Okay, I parameterize it using RT. Okay, I take R prime T. What is R prime T? I take the derivative of that curve. So it's the velocity of the curve, which is the unit tangent. Or the not unit tangent, but the tangent. Okay, so this is the tangent vector. Tangent vector. Okay. The gradient, what? The gradient is not the gradient. Why? The gradient is a function of a scalar field. It's a scalar field. That is Rn to R. But this one is what? R to Rn. All different function here. Okay or not? So this RT, wait, so this RT here is actually what? It's actually split into XT, YT, and ZT. Okay. So R is a function from R to R3. Okay, we don't usually call this a gradient. We just take a tangent vector. Okay. So after you dot, so you dot two vector, you get a number. Okay, but this two vector here, right? This two vector F and dr, okay, or FT here, they are vector depend on point. Okay, so if you dot them together, you also get a number depending on points. Okay, so you get a function of function from Rn to R. Okay, then you integrate it. Yeah, you integrate it. But you describe the R n in terms of parameter equation. So you go have a function from R to R. Okay, so you reduce the work done to integrating a function of one variable. Okay. We will revise this definition on Friday, 3 to 6. Where's the venue? Yeah, 3 to 6. And we will do example on this. Where's the venue on Friday? F4G11, I think opposite. Huh? Why? Cannot pick so many people. Okay, so see you on Friday. 3 to 6.
Hey, hey.
Negative 你再分了，上来一个 negative 你换 direction 再放两个 negative 才变成 negative。
哪里？
因为你换 direction 有一个 negative，
对，没有错。
这个是 positive，因为